Hello, this is Jack Jackson, and I'll be talking today about the Poisson distribution. The Poisson distribution is another family of discrete distributions, kind of like the binomial distribution or the geometric distribution or the hypergeometric distribution. And very similar to the binomial distribution, we're going to be counting the number of successful events over some time interval or some interval. So in a Poisson distribution, the random variable x is going to be the number of occurrences of an event. You might think of that as the number of successes. But it's over some sort of fixed interval. Now that interval oftentimes is time. So we'll say over a particular time interval, whether that's 1 minute or 1 day or 5-minute interval or something like that. We're going to let that interval elapse and count how many occurrences we have of a particular event. Now that interval, like I said, could be time, but there are some other options. It could be distance or area, volume, weight. There's some other things, but we have some set interval that we're going to count over. Now, some of the assumptions for this distribution to work is that the probability that an event occurs is for all units of the same time or the same size. So for example, the same length of time, that the probability of an event occurring in that interval is the same regardless of which interval you choose. So for example, if we're using a 5-second interval, it's the probability that an event's going to occur in any 5-second interval is the same regardless of which 5-second interval we choose. Okay, and of course then we want the number of events in a particular unit of interval, say in this 5-second interval for example. It's got to be independent of the number occurring in another unit. So if the probability on average is that we have 4 events occur in a 5-second interval, then it doesn't matter how many happened last 5 seconds or the 5 seconds before that, the probability that we're going to have 4 events in the next 5 seconds is the same as it was before, regardless of what occurred earlier. And then within that unit of time, the events should be randomly and uniformly distributed. Now, those are the basic assumptions for a Poisson distribution. And of course, as with any distribution, it's useful if we can get a real-world situation that is modeled fairly well by this. So even if the assumptions aren't 100% perfect, if they're pretty close, then we can model it well with the Poisson distribution. Well, it turns out that this is the formula. It's actually a fairly simple formula for the PDF. And again, x is the number of occurrences. Well, the PDF of x is mu to the x power times e to the negative mu over x factorial. Now remember, x is going to be the number of occurrences of the event, so that's going to be a whole number, 0, 1, 2, 3, 4, 5, on up to forever, at least in theory. Mu, as you might expect, is in fact the mean of the distribution. Now, some textbooks like to use the Greek letter lambda. You can see it here. See the lambda right here for the parameter of this distribution. But since it is the mean, we're going to call it mu, and a lot of authors use that notation. It turns out that the variance of this distribution, of course, is denoted by sigma square, as always with the variance. It turns out to be the same value as the mean. So the variance and the mean are both mu. And remember, x can be any whole number, so this is a discrete distribution, but like the geometric distribution, x can go on, forever. So it goes from 0 to infinity, but it has to be a whole number. So there's no way to get x could be, for example, a fraction like a half or something like that. It has to be 0, 1, 2, 3, 4, 5, etc. But notice that the PDF is a decreasing function as x increases. So even though the x can be any whole number, the probability that x is really large is going to be very small. So this is going to trail off and get less and less probability as you go out. Kind of in a similar manner that we had with the geometric distribution as well. And of course this E here is the same E that you probably studied about a little bit in your algebra classes. That's the base that we often use for an exponential function. Okay, so let's see if you can do this. What is the formula for the PDF of a Poisson distribution with mean 10? Go back and figure that out now. I'm going to back up one slide so you can see this and see if you can write down the formula. Press pause now. Okay, now that we're back, if we want to do this, we say the mean is 10, so we just have to replace the mu's here by 10. And of course, this is the formula that we get when we replace the mu's by 10. And so this will be the particular formula for the PDF of this particular Poisson distribution which has mean 10. Now use this formula and create a table for both the PDF and the CDF. Now, of course, this table actually goes on forever. The x's are going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and they just keep going on forever. But let's just go 0 to 10 for the table and figure out the values of the PDF and the CDF. Go ahead and do that now. Press pause. Well, if you use this formula, you should have come up with these values for the table here on the right. X or K is 0 up to 10, and we see the probability there. And notice that it starts very small, gets a little larger, and then eventually it's going to decrease again. So this is pretty typical of a Poisson distribution. It's going to start small, get a little larger, and then come back down, and then eventually the bars get closer and closer and closer to 0. So actually on this particular interval, the probabilities keep getting larger and larger. And of course the cumulative probabilities, all we have to do there is add those up. So we can add up the one to the left. So we can use this formula to figure this out. We can use it directly in our calculator. We can use the calculator to generate this table, or we could use Excel to generate this pretty easily. The rate of occurrences is 10 per unit on average, and that's the mean, so that's mu. And the variance is also 10 as well. Of course, the standard deviation is the square root of 10, which is approximately 3.16. And it turns out the skewness is 1 over the square root of mu, so that is 1 over the square root of 10, or approximately 0.316. Okay? So it's almost symmetric. It's a little skewed to the right with that infinite tail going out to the right, but it's fairly close to symmetric as well. Now we can actually use the TI84 to construct this table or as well, and we can do it by plugging in this formula, 10 to the power x times e to the power negative 10, put all that in parentheses, divide by x factorial. We know how to, by now you should know how to get factorial from the math probability menu. Everything else is pretty straightforward. E is, of course, e to the power is one of the things that you can do directly on your calculator. For many of you, it will be the second and the LN button. But also, this Poisson distribution is actually built in. We have built-in functions for both the Poisson PDF and CDF. So we could actually type this formula right here in Y1 and get this table here. Or we could type in Poisson PDF. Now notice that the inputs are two things. First is the mean, 10, and then the value of the random variable, which here we're going to let be a variable x. So we let Y1 be Poisson PDF. That'll open a parentheses, then you type in 10, comma, x, close parentheses. For the CDF, it's just Poisson CDF. Now, of course, you get those by hitting distribution on your calculator. Okay, and I think that's second variables, and then choose distribution here and up arrow or down arrow until you see the one that you want. Notice that C is Poisson PDF and D is Poisson CDF, so we can put those in. Now to generate the table, once we have these in here in the graphing menu, this isn't the Y equals screen, then we go to the table setup screen. Second window will get you to this screen, and here we want to start the table with X being 0, and we want delta table to be 1, that is delta X to be 1, that is going up by 1s, and put everything on automatic, and then hit table, and you'll see that X does what we told it to do here, start at 0 and go up by 1s. So 0, 1, 0, then 1, then 2, then 3, then 4, then 5, then 6, and we can scroll down this, and here you see the values of the CDF in this column over here and the PDF on the column before. These things in this table agree with the things in this table right here. I actually used Excel to generate the things in this table here. Okay, and then here's what the graph looks like. Of course, it's the graph of the PDF will be a series of bars. Notice they start small, they get larger. Okay, looks like the largest bars are around 10, 11, 9, 10, 11, somewhere in there, the tallest bars, and then it comes back down. Almost looks symmetric right here, but it does have an infinite tail going out here. But they're very, very short bars out here. We can't even see them. The cumulative distribution then is going to be just adding the heights of these bars up, and so of course it starts at 0, 0, and it increases as we go up, and eventually levels off as it approaches 1 as the X goes to infinity. Now, of course, we know that this being a discrete distribution, this is really a step function. So each of these is actually a little horizontal line segment until it steps up to the next level, with a closed dot on the left, open dot on the right. But you can get all the closed dots on the left or what's actually plotted here. And I used Excel to do this. Let's take a look here quickly at the Excel sheet. This Excel sheet here has an introduction to many different finite probability distributions, and I've used this to generate some of the examples that you've seen in the earlier parts of this unit. And this particular Excel sheet is found in the review section of this unit, in Blackboard. And so if you'll go there, you can find this spreadsheet and use it. So for example, right now we're talking about the Poisson distribution. Notice that it's a hyperlinked table of contents there. And this gives you a back to the title page here. So we have some links there that will take us back and forth within the Excel sheet. And here, notice the way this particular Excel sheet is set up, anything that's got a blue background is a defining parameter. Okay, and so those are the numbers that we can change. So in this case, it's changed to 10, and I believe that's what we just had, yeah. And then that will be the rate of occurrences, and that turns out to be the mean and the variance. And the standard deviation there is just the square root of the variance, always. And 1 over the square root of mu turns out to be the skewness, and so I've used those formulas there, so you can kind of see there how those were figured out. So everything's based on this number. Here's the actual formula in general, and here are the values for it. This particular spreadsheet is set up to go through 200 or maybe? Yeah, it goes down to like 200. Now at some point these things are extremely small, on the order of 10 to the negative 180th. So they're very, 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 very small out there, and of course that rounds off to essentially 1. To the limits of Excel, looks like we've already hit 1 by the time we've gone out to about 35. And all I did for the table or in the PowerPoint is I just copied this part of the table up to 10 and copied and pasted over there. And then over here we can see the graphs that go with that. And again, I just copied and pasted those back in PowerPoint. Now, of course, the utility of any particular distribution depends on how we can apply it to real-world scenarios. You know, it's great if we got this nice little theoretical distribution, but it's really only of real practical use if it really models some sort of real-world situation. So here are some examples of situations that are modeled pretty well by a Poisson distribution. A couple examples here, a few examples. The number of traffic accidents per month at a particular intersection. The number of surface defects on a new automobile. The amount, say measured in parts per million, of a toxin found in water or maybe in air, maybe by a plant. So maybe the water that's being nearby a particular plant, we can find out how much toxin is in that. If it's very high, then of course the plant is maybe not disposing of their toxins as well as we'd like. The number of diseased trees per acre of a certain woodland, or the occurrences of any particular thing per acre. Could be the occurrences, number of sightings of a particular kind of wildlife per acre in a certain woodland. The number of death claims received per day by an insurance company, or the number of unscheduled admissions per day to a hospital. So there are a variety of different real-world scenarios that are actually modeled pretty well by Poisson distribution. Let's look at one of them. Suppose that the number of unscheduled admissions per week in a hospital is 20 patients, regardless of the week. What's the probability that the number of unscheduled patients admitted next week will be exactly 7, less than 10, more than 30, or between 20 and 30 inclusive? So we've got 4 different questions there about this situation. Now notice, since there are 20 patients coming in each week on average, regardless of what week it is, they're not necessarily higher or lower on any particular week. This fits pretty well the requirements for Poisson distribution. So we can use the Poisson distribution to model and approximate this real-world scenario. So use the Poisson to answer these 4 questions. Notice that the rate that they're coming in is 20 per week, so that's going to be your parameter mu. On average, we would expect 20 patients in a particular week, so that's our mean or expected value, mu. So let's have you go ahead and work this yourself. We're going to press pause, work this, and then come back and check your answer after you're done. Press pause now. Well, now that you're back, we can take a look and see. And since this is a Poisson distribution and we have a built-in Poisson function in our calculator, we're going to just use that. So if we want to find exactly 17 for a discrete distribution, that's just going to be the Poisson PDF evaluated at that particular value. So in general, when we have a discrete distribution and we want to know the probability that x equals a particular number, we want to go to the PDF and plug in that number. Well, this is a Poisson PDF with a mean of 20, and so since that's built in our calculator, it makes this pretty easy. We just go to distributions, I believe that's second variables, up or down arrow, actually up arrow is a little quicker to get to Poisson PDF. Then you select that, it'll open parentheses there, you type in the mean first, then the x value. So it's 20, 17, close parentheses, enter, and we get that there. So exactly 17, that probability is 0.07595, etc. Probability that is less than 10 means less than or equal to 9, because remember this is discrete and it's only whole numbers for this, so it can go up to and including 9. And so remember, a CDF, what it does is it gives you the cumulative probability up to and including that, and that's exactly how the Poisson CDF function in the calculator works. So if you do Poisson CDF of 20, 9, that will be the probability that x is less than or equal to 9, which is the same as the probability that x is less than 10. That's what we're looking for. And we see that that's 0.00499 Probability that it's more than 30, that means not less than or equal to 30. So with that will be the complementary probability. So you can do that as 1 minus the probability that x is less than or equal to 30. So it's 1 minus, actually that's off. That should go more than 30 does not include 30, so 30 should be subtracted. So this should be 1 minus Poisson CDF 20, comma 30. I'll change it actually on the spreadsheet probably by just changing this 30 to a 29, and then the answer will be correct. I'll change that on the handout for this. So probability that more than 29 will be 1 minus Poisson CDF 20, comma 29. Between 20 and 30 inclusive. So now we want to include 20, between 10 and 30 inclusive. So you want to include 10, include 30, and everything in between, but exclude things that are less than 10 and exclude things that are larger than 30. So notice if we do Poisson CDF 20, comma 30, 20 is our parameter, mu, which is 20, and then 30, that will give us the probability up to 30, including 30. But then we want to subtract the ones that are less than 10, so that would be the ones that go from 0 to 9. So then we want to subtract off the Poisson CDF 20, comma 9. And when we do that, we get 0.9815299. So about 0.98153 is the probability that's between 10 and 30. So over 98% of the time, the number of patients per week will be somewhere between 10 and 30 inclusive. Very rare to get one more than 30, because that would be only about 2% of the time that happens, and even less likely to have less than 10, which is probability of 0.5%, very small. So that gives us some ideas about Poisson distributions and an example of an application there.